Okay, I'm starting the slideshow. Okay, my name is Ramkumar Manavalan. I've been in IT industry for since 2001, and I started programming um, since I was studying 10th standard. Uh, little early when you consider that period of time in the computer era, 1995. Hardly any computers around, but I started programming from that age, and three things that have always fascinated me in the programming world, um, which is uh, the first one was the logical programming paradigm. Uh, that was very interesting because you get to solve programs and problems logically. Okay, Harun, are you trying to convey something to me? Because I see some annotations on the screen. Okay, okay, I'll proceed. Three things that have fascinated me in the programming era world are first one was logical programming. My very first, very favorite programming language was Prolog. I'm not sure how many of you heard about that. It's a logical programming paradigm where you can solve problems in the logical way, right? If some of you have time, please go look at what Prolog is and logical programming paradigm is. That's very interesting and very fascinating. And the second thing that fascinated me and still fascinates me is the recursion. That's a true marvel. And even after so many years of my IT experience, that is still in my list of fascination in programming. And the third one is the reactive programming, which is catching up very fast now, which also includes some of the functional programming concepts where you can write code that can scale, right? That is very, very interesting. And that's very fascinating. So recursion is something that is very, very close to my heart. And I've done a lot of classroom, small to big trainings on this topic. But this is my first webinar. So please forgive me if I have not followed any of the protocols of webinar. Okay. Thanks to GUVI. GUVI is doing an amazing job in having this social initiative during this lockdown period. I think students are benefiting a lot from this, and I'm very glad to be one of the contributors to this social initiative. Thank you so much. And I work for a company called Arca Insurance Broking, and we developed a product called monkeycab.com, which is basically an online portal where you can buy your motor, car, or bike policies. And in the future, you can also buy health and travel policies. We're very, very similar to Policy Bazaar, CoverFox, ET Insure kinds. So when you get time, please also explore monkeycab.com. Okay, without further ado, let me go into this. So the power of recursive programming is actually a part of a bigger topic, which is problem solving. This is my two-day course, and the power of recursion is a very, very small topic in the problem solving topic. So problem solving is to do with how to use the various algorithmic design strategies to solve various kinds of problems, what to pick when, etc. And last we will look at the time complexity analysis for recurrence relations, because this is one of the very challenging things for programmers, because when they can write recursive programs, they still face the challenge of how to arrive at the complexity or the upper bound or lower bound of that particular algorithm. So I'll also explain how easy it is to analyze the time complexity of algorithms that have recursion in it. Okay. And one disclaimer before I get in, if you may be averse to recursion, or you may be already liking recursion, or you might have been a very hardcore iterative programmer, doesn't matter. For this 1 hour, please keep your mind blank and try to understand what I'm saying. So you will definitely appreciate why recursion is important. And this learning is going to be based on the simplification, where how to master recursion in a simplified manner. This is especially for people who think recursion is complex very difficult, very challenging. It is not so if your learning methodology is very simple. Okay. Okay. The power of recursion. So very quick comparison between iteration and recursion, because this is a very, very debatable topic. Let's look at an example. In general, for few basic cases, iteration is simpler than recursion, especially when you have to visualize, think, and code. For example, you're given a problem, and it's very easy to think or visualize how your solution must be, and also write the corresponding code for that. So iteration is simpler when compared to recursion, I agree. For example, simple factorial, right? This is the iterative approach where I have a for loop and I just multiply the numbers and I print. And the same using recursion for a newbie, for a first time person in programming, it is a little difficult to comprehend or to visualize what is happening, right? Okay, I see voice is breaking for some person, but not for the others. Harun, can I proceed or should I pause here? Okay, I'll proceed. So recursion, as you can see, the two simple programs, recursion is slightly difficult or not simpler to visualize, think, and quickly understand what's happening, right? Whereas iterative is very simple. So then why do we have to use recursion? Is the question. Let's look at the example of tic-tac-toe. I think most of you would have played tic-tac-toe in your life. Let's try to solve tic-tac-toe from the computer perspective, like a player and a computer playing against each other. And you will have to write the code for the computer program. Okay. You can use a rule-based strategy where you examine the position of the current board, determine the open positions that you can play with. Based on the current position of the board, you can actually write some rules and you can decide the best move. I'm sure it's very easy. You can easily write a winning strategy, or at least write a strategy that will not let the computer lose, if not win. Okay, that is very easy. And that does not necessarily require recursion. Okay, you can always write a rule-based strategy very easily. But what if your rules have bugs? When and at what point in time you will be 100% sure that you've covered all possible cases, all possible scenarios. What if a particular case breaks and you have not coded or thought about it? And what if the board size is not 3 by 3, which is a legacy tic-tac-toe? And what if the board size is n by n? Will you be able to still play around the same rule-based strategy, or how will you change the rules? And if it is n by n, how many more cases you have to think to avoid all possible bugs? Further, what if the board size is n by n and the number of players is not 2 but is m? What if 10 players can play a 100 by 100 tic-tac-toe? Will your rule-based strategy be helpful? Or will it be easier or simpler? I don't think so. So you will have to do a lot of backtracking. You'll have to do a lot of decision making. You will have to do a lot of sub-probleming in tic-tac-toe so as to find the next best move when the board size is 50 by 50 and the number of players is 5 or 10, right? So you'll have to do a lot of backtracking, decision making, sub-problem. So recursive programs may not be simpler, but they express more naturally than iterations. We'll come to this point of what express mean with some example. But in such complex situations where you cannot take down a paper and write down all possible rules and ensure that you do not have any bugs in it, it is hard. So recursion comes to your help in such cases. Okay, let's look at merge sort. Most of you must have studied or learned merge sort, but I'll quickly explain for the benefit of people who have not learned it. So this is a sort algorithm that basically splits the items to be sorted into two groups, left and right, repeatedly, sorts each group and merges them into a final sorted sequence. So let's look at this example. So you have a full list from 38 to 10, and you break down the list to two equal halves, left and right, and then you keep doing it for until each list is having only one element in it, which means it's a sorted list. So when you look at the middle row where you have 38, 27, 43, 3, 9, 82, 10 as separate lists, that's when you are very sure that each list is sorted on its own. Now all you have to do is merge these smaller lists, say merge 38 and 27, you know which one to put first. And merge 43 and 3, you know which ones to put first. And now when 2738 list and 343 list have to be merged, what you have to really do is very simple, because you know that these two lists are already sorted. So you just do a simple merge. You pick 27, see if it is lesser than 3. Yes, put 3. So you know these two lists are sorted, so the merging is going to be a little easier. And you're going to do it in order of n times, not order of n square. Okay? And when you keep doing this, you get the sorted list back. Okay? And because most of you know merge sort already, and I did this quickly. So now let's look at how merge sort can be implemented both iteratively and recursively, and see how recursion is slightly better than iteration. So this is the iterative approach. I took this code from Geeks for Geeks. So this code should be working fine. I have not tested it, but it should be working fine. They have two while loops. One is nested in it, and they do the same splitting operation of right and left, and they merge, and then they keep doing it until the list is sorted. So they have two nested while loops. If a programmer is looking at this kind of code for the first time, that programmer will have to, spend quite some time to understand what's exactly happening. Say if I ask you to review this code for its correctness, if I have to ask you to check if this code has any bugs or not, it's not going to be an easy thing for you. You will have to pay attention to each and every part of the code, and how the loops are nested, and how the variables are actually passed around, etc. Whereas I just show you the recursive implementation of the same thing. It's much simpler and hardly any logic in it. And you're able to easily understand what's happening, except for the recursive part, right? So now, what are the differences between the iterative code and the recursive code? The recursive code is slightly more higher level. Say you have the hardware, and then you have the assembly programming language, and then you have the higher level programming languages, etc. And within higher level programming languages, recursion is even more higher level than iterative. What I mean by higher level is it's even more verbose, even more, I shouldn't say verbose, it's even more expressive than iteration. If you look at the description of merge sort in English, where you see on the top of this slide, a sort algorithm that splits the items, blah, 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 right? You can the same text can be visualized in the recursive code, whereas the same text cannot be visualized in the iterative code. You see the point? So that way, the recursive code is even more higher level programming. It's even more expressive. It's even more interesting for the humans to understand. Because it is easier to understand, it's easy to maintain. And if you have to change something in it, or if you have to check for its correctness, it's going to be very easy for me. It is lesser prone to errors. The only challenge among these two in terms of recursion is that A programmer who has been very experienced in iterative approach will find it a little difficult to understand why those two calls are there, one below the other, and when will that merge function be called, etc. Because that person is not used to recursion, that's all. But once you master recursion, once you understand or once you are able to visualize how recursion works, then obviously the right hand side is the best fit for this merge sort implementation. So in terms of maintenance, in terms of lesser errors possibilities, and in terms of higher level programming, recursion is always the best for merge sort, for the merge sort case. So what are the advantages of recursion over iteration? It is relatively lesser prone to errors, as you don't have to write complicated logic, complicated condition blocks, complicated arithmetic operations, complicated while looping constructs, when to break, when to continue, etc. Not required. And it's more maintainable because fewer lines of code, more natural, more expressive. The problem statement is actually seen in the code. You don't have to play with all these variables, arithmetic operations, blah blah blah. And it is best fit for problems that involve backtracking, subprobleming, nested composite structures, etc. So what you saw in merge sort is a classical case of subprobleming. So you have a bigger list. You split the list into two smaller problems. Now apply the same logic for each of these smaller lists. So one problem is broken down to two subproblems, and that subproblem is again broken down to two another subproblems, etc. And the same way for the merge also. You have two sorted lists, you merge. And that sorted list is again merged with another sorted list to get the even longer sorted list. So merge sort is a classical case of subprobleming, and in those cases, recursion is a better way because it is more natural and expressive, easy to understand and easy to maintain. And the other hidden advantage of recursion is that data is managed in function stack. Whereas in iterations, you actually have to manage data using your own data structure. This is not that it's very evident for all programmers, but if you actually understand this, then you can understand recursion very easily. So where is the data here? The data is actually in the function stack. We are calling functions recursively, say 100 times in deep. And where is the data stored for each of these 100 function calls? It is in the function stack. So this is a very big advantage. Whereas if you use the iterative approach, you will have to maintain that data structure on your own. You will have to maintain the stack operations or the queue operations or whatever tree operations or whatever by your own, which is again making the program more error prone and more difficult to understand. Yes, there are few overheads in recursion where, because you make a lot of function calls, there is memory overhead. You can solve that using tail recursion. We'll also see an example of tail recursion in the further slides. Using tail recursion, you can actually manage memory. And if you adopt memoization, even the time complexity is also managed because you don't solve repeated subproblems, which can be seen in some cases. In merge sort, you don't have that repeated subproblem cases. Whereas in some problems, you will have the repeated subproblems. And we'll also look at an example of this memoization in the further slides. So if you manage recursion properly using tailed recursion approach or using memoization, then you can get rid of the overheads or the consequences of recursion and get only the benefits of recursion. So the verdict, according to me, which is still debatable, is if you are expert in both recursive and iterative programming, then you will choose the most natural fit for a given case. If you're an expert in only iterative programming, and if you're not master at recursive programming, then what you will do is you'll try to force fit iteration in all cases where recursion is a better fit, and the vice versa. Somebody who is extremely conversant in recursion, somebody who is very good only in recursion will always use recursion for cases where iteration is the best. But what I would suggest is master both of them. Most of you would be already experts in iterative programming, but what I would suggest is master recursive programming also. Then you take a call for each situation on what's the best style to apply. So I'm proud to say that I'm a master in both of these. So given a problem, I know whether I should think recursively or I should think iteratively for this particular problem statement. And I am not a blind follower of recursion or a blind follower of iteration. So unless you master recursive programming, you will not be able to make a decision. So make an attempt to master or become an expert in recursive programming. And that comes only by solving a lot of problems using recursion, not by studying or not by watching only webinars like this. You must actually get your hands dirty and you must solve all the problems by yourself using recursion. Okay, very quickly, I'll spend 5 to 10 minutes on the foundation for people who have not heard about recursion or who have not understood recursion in deep. Okay, what are the foundation points for recursion? So recursion is the basis of all such problems. To think recursively is the key. It's not about programming. You should be able to think recursively. Given a problem, how do you think recursively? And I'll give you some techniques during the skills slides. So there are 4 questions that you must answer for any problem that needs to be solved recursively. First is, can the problem be broken down to subproblems? When I say subproblem is again the same nature as the original problem, except that the size is reduced a bit or the complexity is reduced a bit. So in case of merge sort, you originally had a list of say 7 items. And when you split that into 2 lists, you have now 2 subproblems. And each of these subproblems are of size lesser than the original problem. But this subproblem has again the same problem as the original problem, which is to merge sort. So given a problem, you have to ask yourself if that problem can be broken down to subproblems. First question. Second question, is there a recursive composition? This is a little tricky. I'll explain that with an example. So if you look at problem A and you have subproblem of problem A. If you have learned OOPS, then you can understand is and has a relationship. So subproblem of problem A is again a problem A because they are of the same nature. Okay, and problem A has subproblems. For example, in merge sort case, at any point in time, a problem has 2 subproblems because we're splitting the problem into 2 subproblems. So in merge sort, the original problem has 2 subproblems, and each of the subproblems is again the same problem. So is this kind of recursive composition available or pictured easily? Then you can do this recursion. Third question you must ask yourself is there a terminating condition or the base case? So in case of merge sort, the terminating condition was when the list had only one element. So when the list has only one element, you cannot break that problem into further subproblems. So that is a terminating condition, and that's why you must have the returns. That is the base case for this recursive program. Is there a logic that reduces the other cases to base case? So this is the recursive part. So whenever the number of items is greater than 1, you can always split the list into 2 and then again apply the same thing, right? So these are the 4 questions you must ask yourself before assuming that recursion can solve the problem. So a very simple example is factorial again. So in factorial, 4 factorial is nothing but 4 times 3 factorial, right? So here the subprobleming is that you take out 4 and you apply the same technique for the 3 factorial. So 3 factorial is a subproblem of 4 factorial. 2 factorial is a subproblem of 3 factorial, and so on. So what is the base case here? Terminating condition when you reach 1, because you cannot subtract 1 further. So 1 factorial is 1, so that is the base case. Now apply the same or answer the same 4 questions for Fibonacci number or binary search. I'll wait for 5-10 seconds for you to think. So in case of Fibonacci number, it's very simple, because f of n is equal to f of n minus 1 plus f of n minus 2, right? So f of n is f of n minus 1 plus f of n minus 2. For example, if I want the 8th number in the series, okay, that's basically the sum of the previous 2 numbers. So I calculate f of 7, f of 6, I add those two to get f of 8. So this way I'm doing subprobleming, where I'm splitting each problem into 2 subproblems, and I aggregate or I merge these 2 subproblems by addition. What is the terminating condition here? When n is 0 or 1, I return just the n. I cannot break that problem further down. So there is recursive composition, because f of n has 2 subproblems, and f of n minus 1 and f of n minus 2 are again the same problem, which is f of n, Fibonacci number. Okay. Same for binary search, where the terminating rules are: when you have found the element, that's a terminating condition, or when you have not found, which means you have no more nodes to traverse. You have traversed all possible nodes, then you cannot reduce any further. So what is the subproblem here? At each node of the tree, you compare the element to be searched with the node element. If it is lesser or greater, depending upon that, you go to the left subtree or the right subtree. Now, when you go to the left subtree, then again the same problem exists. Do the same logic that you applied for its parent. You keep doing this. So this is the subprobleming approach. So once you reach the terminating conditions of the base cases, you stop. So we got answers for all the 4 questions in terms for Fibonacci number and binary search. So recursion can be easily applied. So one difference between these two is that in Fibonacci number, at each point in time, you're actually subprobleming twice. So there's a branching recursion. Whereas in binary search, it is a linear recursion. At any point in time, you actually go to only one subproblem. Factorial, binary search are examples of linear recursion, whereas Fibonacci number and merge sort are examples of branching recursion. So if you are new to recursive programming, you can do things like this to understand what exactly is happening. So printf factorial of 3 actually executes 3 star factorial of 3 minus 1, which again does 2 star factorial of 2 minus 1, and you reach the terminating condition, which is returning 1. You go back and you print. Okay, either you can do it on your paper, or you can use things like pythontutor.com. I came to know of this from one of my teammates. This is a very handy tool where you can actually visualize how the code execution happens, or any other debugger, visual debugger for that matter, can be used to understand how recursion works. Okay. As I said in the beginning of the session, this is the most interesting, most important aspect of this webinar. I want you to understand what skills are required to master recursion, because unless you know what skills are required, it's very difficult to easily learn recursion or simplify your learning of recursion. Okay. And as I said earlier, these skills are derived by me based on my experience after doing it all by myself, after teaching recursion to a lot of people, and the feedback, what kind of learning impediments were there with them. And so focus on these skills and you can learn recursion very, very quickly. Okay. The first is you must be developing the skill of generating combinations or permutations in the form of trees or graphs. Because most of the backtracking problems, most of the subprobleming issues, or most of the decision-making problems will demand you to think about combinations and permutations. You might have heard of questions like, think of all possible ways to generate, find out all possible routes, find out all possible combinations, find out all possible solutions. All these are easier only if you're able to visualize those combinations or permutations in the form of trees and graphs. The moment you are able to think or visualize the combinations in the form of trees and graphs, then the coding part becomes easier for you. We'll do some examples on how to master this or to explain to you how to better do this generation. We'll look at some examples very shortly. The second skill is identifying subproblems of a problem. So given a problem, how do you identify the subproblems? This is not a very big, very difficult skill, but not all of us do this actually. It's very easy. Given a problem, you should be able to easily arrive at how can you classify or how can you divide this problem into subproblems. Again, I'll give you some examples on this in the further slides. The third skill, which is even easier, is how do you view a problem both top-down as well as bottom-up? For example, in factorial case, you are given the problem of finding factorial of 5. So the top-down approach is you start from 5, you go to 4, you go to 3, you go to 2, you go to 1, and then you again come back, multiplying, and you get the factorial of 5. The bottom-up approach of the same factorial is you start from 1, you multiply the next element 2, multiply the next element 3, 4, 5, 4, and so on until you reach n. So this is bottom-up approach. This is very important, not in all cases, but in few cases, especially when you have to decide between divide and conquer or dynamic programming, or within dynamic programming, what should you do? Should you apply top-down approach or bottom-up approach? So your efficiency or the time complexity analysis will be easier if you are able to visualize the same problem, both top-down as well as bottom-up. Note that most of the problems can be solved either using top-down or bottom-up. So some problems are better solved using bottom-up, some problems are better solved using top-down. So you should be able to master this skill also. Whenever you face a problem, whenever you read a problem statement, try to see how to solve it top-down and how to solve it bottom-up. Okay. So let's deep dive into the first two skills further. I got a note from one of the audience that the audio is not clear. Harun, can I proceed if the audio is good? Okay, I'll proceed. Okay, skills to master tree or graph. An example. Say I give you a task of converting this table to a tree. Sridhar, I think you're saying YouTube audio is good. I don't get it. Hello. Hello. Can you hear me? Okay. Sorry for this. Let me proceed because you have lost some time in this. Okay. So skills to master. So if I have to ask you to convert this table to a tree, so this table has say 8 values starting from 000 to 111. Okay. So if I have to ask you to convert this representation from a table to a tree form, how would you think? Because oftentimes you will deal with such patterns, right? That's a very interesting pattern here, right? Binary digits, and you flip the zeros and ones. There is from zero, basically from 0 to 8 or 7, right? 0, 1, 2, 3 up to 7. There's a pattern here. So oftentimes you will encounter such patterns in the problems that you're solving. So instead of the legendary or the traditional way of storing them in table and processing them in a table or a list, what if you start thinking from the tree perspective? So how will you convert this table to a tree? So first you have empty list. Then you have a choice of either choosing 0 or 1 for the first digit. Say I choose 0 for the first digit. I have the option of choosing either 0 or 1 for the second digit. So now it is either I got the combination 0, 0 and the combination 0, 1. Now for the 0, 0 combination, I again have a choice of 0 or 1. So I get 0, 0, 0, 0, 0, 1. So same way for 0, 1, where I get 0, 1, 0, 0, 1, 1. I get 1, 0, 1, 1, so on and so forth. Now if you look at the leaf nodes, you got the exact values that you see in the table. So these are just two different forms of how you deal with the same set of values. Either you have a table with a list where you iteratively go ahead, or you have a branching style where at each point you branch and decide where you want to go. For example, now if you have to process only those that have 1 in the middle, right? Then I can choose the appropriate branching strategy in this tree. And I'll have a different strategy for the table structure as well. But in some cases, the tree traversals will be faster and quicker and even more expressive or natural to traverse. So now, what does the depth signify? So what is the depth of this tree? It is 3, right? So what does depth signify here? It's basically the length of the text. So the length of text is 3 maximum. So the depth is 3. So when the length of the text is 5, then I'll have to go 5 levels deep. So if I have to go to a particular element, I'll have to do only 3 traversals in a tree. Whereas if I have to go to a particular element in the table, I may have to do 7 traversals or 7 iterations, correct? So you're decreasing the iterations or the number of traversals by logarithmic way. So what does max children signify? So what is the maximum number of children for any node in this particular tree? It is 2 because it's a binary tree. And why is it 2? So what does that signify? Why is it not 3 or any other n? Why is the number of children for this tree 2? Because it corresponds to the size of the given set. You're choosing only from a set which has 0 and 1. So the max children is the size of the set. So in a problem that you encounter, if the set size is 3, for example, I can choose 0, 1, or 2, then the number of maximum children will be 3 and not 2. So the depth and the max children determine the efficiency of your algorithm when it comes to trees. And these two factors correspond to the actual problem statement. So given a problem, you try to map the problem statement details to the tree artifacts in terms of depth, max number of child allowed for a particular node. So what if I want you to convert the following table? I have 0, 1, 0, 0, 0, 1 all the way up to 111. Here the length of the text is not fixed to 3. It can be 1, 2, or 3. So in that case, the same tree holds good because instead of just looking at the leaf nodes, I look at all nodes of the tree. Every node, if you look at every node and traverse in print, you get the entire list. Let's look at more examples. So you have a bag full of gold, silver, and bronze coins. Okay, unlimited number of coins. And if I have to pick 2 coins, what are the various possibilities of coin types I would get? A very simple problem. Okay. In fact, if you're trying to solve real world problems, it will be of the same nature, but in different magnitude, different dimensions, that's all. But this is a typical possibilities problem. What are the various possibilities of coin types I would get? Okay, so how do you visualize this in the form of a tree is the question. Because here it is just gold, silver, bronze. And the problem statement is talking only about picking 2 coins. Whereas in real world problems, this won't be just 3 or 2, it will be really huge number. But given this problem statement, how will you think from the tree perspective? How will you represent this particular thing? How will you generate the possibilities from the tree perspective? So this is an example. So I have an empty node and I have the option of choosing either gold or silver or bronze. I can get any of these 3, the first pick. And once I pick the first coin, say in case I pick gold, the next pick I may again get a gold or silver or bronze. So gold, 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 silver, gold, bronze is a combination possibility that I get. Similarly, SG, SS, SB, BG, BSB. So if you look at the leaf nodes, we get all possible coin types. So what is the depth of the tree? 2, because I'm picking 2 coins, the length of the text, right? And why is the tree not binary? Because at each point in time, I have 3 options to pick, not 2. In the previous example, you saw 0 and 1. In this example, you are saying 3, gold, silver, and bronze. So this is not a binary tree anymore. This is an n-ary tree. Okay. So instead of this, what if I ask you to generate only the combinations that you see on the right side of the slide? So what's the difference between the leaf nodes and this table? Because what you see on the right side as a table is the combinations, whereas what you see as leaf nodes is the permutation. The order matters. So gold, silver, and silver, gold are the same. So we are removing those 2. Gold, bronze, and bronze, gold are the same. So we are removing. So what if we want just the combinations, not the permutations? So how will the tree look like now? So once you pick gold, you have the option of picking gold against silver, bronze. But once you pick silver, you don't have to worry about gold, because there's a case already available where you have picked gold and silver. So in case when you pick silver now, you only worry about silver and bronze in the second pick. The tree is still the same in terms of depth. The tree is still the same in terms of the number of max children, but we are saving a lot of nodes on the way. For the same thing, you can have one more way of representation where you can have a binary tree. For the same combinations, where order doesn't matter, you have an alternate strategy of using a binary tree. So look at this. You have an empty list, and you have a choice of either picking or you have a possibility of either getting gold or not getting gold. In case you get gold, in the next option, you either get a gold or you don't get a gold. And now you got gold, so you're fine. In the case where you do not get a gold again, you again have a possibility of picking silver next or not, and so forth. So in this case, the tree is having maximum number of children as 2. It's a binary tree, but the depth has increased. So this is not a wise strategy of visualizing the tree for the combinations, because it is deeper, which means the depth is longer. It's very unbalanced. Unlike the previous tree, this is not very balanced tree. There are too many nodes, and the leaves have unnecessary items. The leaf nodes have just silver, just bronze, just gold, and you don't want all those things. So even when you think about tree, or when you visualize tree, you should know what is the right way to visualize. A binary tree or n-ary tree, the depth matters, whether it's balanced or not matters, number of nodes matters, and what you see as leaves matter. So when given a problem, think of the best way of visualizing the tree. Okay, let's look at one more example. So this is a house robber puzzle, very common puzzle, but I'll explain still for people who don't know. So there are n houses in a line, and each of the house contains some value in it. So a thief wishes to steal from a few of these houses, but the thief cannot steal from two adjacent or neighboring houses. Okay. So if he steals up house 1, then he cannot steal house 2. So given this situation, what are the possible combinations of houses that he can steal? Is a question. So given houses say 1, 2, 3, 4, what are the possible combinations of houses that he can steal without violating the rule? Right? Let's visualize this from the tree perspective. Say let's take an example of n is equal to 4. So there are 4 houses. Okay. So now the thief hasn't robbed any house. So now he has the option of either robbing the house 1 or not robbing the house 1. Okay. So now there are two possibilities. Suppose he has robbed house 1. Now what is the out of the options left? He cannot rob house 2. He can rob house 3, or he cannot, or he doesn't rob house 3. So in case he robs house 3, then you get this 1, 3. And in case he doesn't rob house 3, you just have the combination of having robbed only the first house. So in case of 1, 3, the thief cannot rob 4 again. So that ends there. So in case of the other node 1, you have the option of robbing 4 or not robbing 4. So the decision that you're taking at every node is, of the remaining houses, am I picking that house for robbery or not? That's the decision I'm taking at every particular node. And because the decision is 2, either I rob that house or I don't rob that house, the max children is 2. So same way for the other side, where I don't decide to rob 1, I rob house 2, and blah, blah, blah. So if you look at all the leaf nodes, that will give you the possible combinations of houses. So the thief can rob houses 1, 3, 1, 4, or just the house 1, or 2, 4, or 2, or 3, or 4, or not rob at all. So you have all possible combinations listed here as leaf nodes. So the same problem is now visualized as a tree. The next challenge for a programmer is, how do you convert this tree into a program, into a recursive program? So when you are at the root node with empty array, what is the problem statement you have in hand? You are given a list of houses 1, 2, 3, 4, and you have to pick either house 1 or not pick house 1, and then go further. Once you pick house 1, you come to a sub problem where now the problem in hand is, I'm given houses 3, 4, because I cannot choose 2 because 2 is already adjacent to 1 and 1 is already picked. So when I come to the 1 left node, the problem is still the same, where I'm given the houses list 3, 4, and I should either pick the first house or not. The same exact problem that you had in the root node, except that the root node had 4 houses, and this subproblem had only 2 houses. So at every node, you are actually dividing the original problem into 2 subproblems. And you apply the same logic again, right? So when you understand this, it's very easy to visualize the code. This is all the code. if you look at the list of the function called list robbable houses, I initially pass an empty array and the number of houses 1, 2, 3, 4. So the list robbable houses has two parameters. One is picked and the other is remaining. Okay, and this is a terminating condition where if there are no houses to pick, I quit. If not, if the remaining houses to pick is non-empty, then I come here. In the first subproblem, I pick the first element from the remaining of 0, and I pass the remaining list to the function. In the second, I don't pick it. The picked is still the same, but I move to the next. I remove that house from the list, so the remaining is now from the adjacent houses. So the problem statement is conceived as a tree, and what you're doing in the tree at every node is actually in the program. So once you start thinking like this, you'll be able to understand further. And more important is when you look at some code like this, or when you accidentally end up writing some code like this, try to debug and find out how it works. So in this case, which possibility is generated first? 1, 3 is generated first, or 1, 4 is generated first, or 2, 4 is generated first is the question. So in most cases, it would be depth first. In some cases, it would be breadth first, depending upon how you're arranging the recursive calls. So here you're actually dividing the problem into two subproblems at each instant. Okay. And one more case is where when you solve arithmetic expressions, you will have a structure like this, where here you have the operand as plus, you have the operand of minus and multiplication. So the expression is actually divided into smaller subproblems. First, you calculate 12 minus 7, then you calculate 10 divided by 10 multiplied by 2, 50 divided by 5, then put them all together, and then it recursively composes. So this is a very classical design pattern called composite. Have a look at it during your free time. And because I don't have a lot of time, I'm going to skip this. Where how do you visualize a particular tree? If it is a binary tree, it is very simple. You have a left child and right child. And if it's n-ary tree, then you should have a list of children. And there are more interesting ways to represent a tree where you have a parent node pointing to a child, and that child has siblings. So the structure looks like this. The tree has leftmost child, and it also has a list of siblings. This is another way of looking at tree. For some problems, you may have to think of representing a tree like this than the traditional way of having list of children for each node. So Fibonacci number is again a tree, but a difference is here when you solve problem 6, you're actually solving problem 5 and 4, right? And when you solve problem 5, you're solving problem 4 and 3. So problem 4 gets solved twice. So problem 3 gets solved more than twice. Problem 2 gets solved more than thrice, right? So in this case, it's more a graph than a tree, because in a tree, a node cannot have more than one parent. Whereas in this particular structure that you see, a node is having more than one parent, so it's a graph. So in some cases, you'll have to think in terms of graph and not tree. So what you actually have achieved here is memoization, where because you solve problem 4 only once, and next time a problem 4 is requested to be solved, the result is returned. So you actually memorize here. So the point is that not every time should you think about trees, but some cases you will have to think about graphs also. Okay, very quickly on subprobleming skill, let's look at some examples. So the questions you need to find answers for in order to arrive at whether the problem can be divided into subproblems is What are the subproblems that you can visualize? What is the base case or end of subprobleming? And how to aggregate or conquer. After you solve the subproblems, how do you aggregate the results to solve the original problem? Okay, let's look at some examples. Fibonacci, what are the subproblems? The previous two numbers. If I have to solve Fibonacci of 6, I'll have to solve Fibonacci of 4 and 5. So those are the two subproblems for this problem. So it's always the previous two numbers. Okay. And what is the base case? When you reach 0 or 1, you cannot divide the problem further. And how to aggregate? You simply add. Once you solve the two previous subproblems, you just add. F of n is addition of f of n minus 1 and n minus 2. So which means you have got the answers to all the questions. So Fibonacci is a very classical case of subproblem. So you can apply subproblem strategy here. Merge sort, you already saw. What are the subproblems? You say divide the subproblems into two R's, left and right. What is the base case? When the list has only one element. And how to aggregate? You merge. Once you reach the base condition, you merge the sorted list. So that is the aggregation or conquering strategy. Okay. A quick thing on tail-end recursion, because I already told you the tail-end recursion is one of the optimization technique to avoid memory overheads. So this particular factorial function is actually doing a check if n is greater than 1. If it is greater than 1, then it does the n multiplied by, again, calling the factorial of the previous number. In the base case, it is returning 1. So what is tail-end recursion actually is? So as the term says, the recursive call you make inside a function should be at the tail end. So if you look at the function above, you're returning 1 in the base case. That is something that you can ignore because that will happen only once for any function call. What happens multiple times is the return n star factorial of n minus 1, right? So when 5 is passed, you do 5 star factorial of 4 and so on. So in this case, the last thing that the function does before returning is multiplication. So it multiplies n with what is returned from the factorial of 4. So the last thing that this function does is multiplication. But whereas what tail-end recursion says is the last thing that a function should do is actually the recursive call. The reason why this has to be done is when the last thing that the function does is the recursive call, then the compiler does not have to store the stack frame for each recursive call. For example, if I'm doing a multiplication or if I'm doing a lot of logic after the recursive call, then the entire thing must be stored along with the data in the stack frame. So every function call, the stack frame grows, so the memory keeps growing, sometimes exponentially. So when you write a recursive program which runs for like 1 million nodes or 1 million times recursively deep, then there's a possibility that your stack will overflow and your program will crash. Whereas if you make all your programs tail-end recursive, which means the last thing that you do in a function is the recursive call, then you don't keep adding the memory for each function call, recursive call. So you consume lesser memory. So your program is set to run longer than if it is not tail-end recursive. So every recursive program that you write must be tail-end recursive to the best possible extent. So for example, the factorial can be made tail-end recursive like this, where I return factorial of n minus 1 n star output. So what the last thing that I do is the factorial, the recursive call itself. I'm not doing anything on the result of the factorial. I just return it. So the right hand side code will take lesser memory because the stack frame doesn't grow at each call, whereas the left hand side will consume a lot of memory. So think about this whenever you write recursive programs. Okay. Uh, the last topic for today's webinar is the time complexity. As I said earlier, um, so before that, let me brush through the skills required. The skills required that I said were, how do you visualize a particular problem in the form of a tree or a graph? And how do you, given a problem, how do you think in terms of the sub-problems? And how do you think about aggregating the sub-problems? And the third skill that you require is the looking at the problem both top-down as well as bottom-up. Okay. So let's go to time complexity very quickly. Probably I'll take another 10 minutes and I'll wind off. And I assume all of you know what complexity means. So I'm not going to talk about that. And in today's, the next 10 minutes, we'll talk about the upper bounds, not the lower bounds or the tight bounds. Okay. And I'll rush through. So in case you don't get it completely, it's okay. It will be an awareness to you. You can always read further, but try to grab as much as possible. So in case of recurrence relations, I mean recursions, you can use something called master theorem. I think most of you must have read master theorem in your algorithm data structures or some other subject in your college. So master theorem provides an asymptotic analysis for recurrence relations. So it is mostly for problems that require divide and conquer strategy. So what the theorem states is the time complexity for a given problem of size n. Okay, T of n is basically the time complexity of a problem of size n is nothing but a times T of n by b plus f of n. So what is a here? A is the number of subproblems that you divide at each stage. Okay, and each of the subproblems now have the size of n by b. For example, in case of merge sort, what did we do? We split the subproblem into 2 at each time. So A is 2. We're splitting the problem into 2 subproblems. And what is the size of each of the subproblem? It is basically half of the original problem. So B is 2. So you're dividing the size of the problem by 2. So 2 subproblems, each having size half of the original problem, is for merge sort. And what is f of n? It is the time required to create the subproblems and combine the results. Basically identifying the mid of the list and then dividing the list into 2. And once the lists are sorted, then you merge the sorted list. So all the time required for that is f of n. So the time complexity for the problem of size n is nothing but number of subproblems you split at each time and the time taken for that particular subproblem. And at each instance, how much time you take for creating the subproblem and combining the result. Let's look at some examples. Factorial. So in case of factorial, so what you basically do is you have some basic operations of multiplication, comparison, subtraction, blah, blah, in addition to the recursive calls. Okay, let's call them, as let's count them as 3 units for now. It takes 3 units of time to do all those overheads. Okay, which is f of n. So now what is base case? T of 0 is 1. When you have reached the last element, then you have to do only returning of 1. So the time complexity for the last base case is just 1 unit. Okay. So let's look at T of n. T of n is nothing but the time taken for solving n minus 1 plus 3. 3 corresponds to the red underlined ones where you have to, the overheads of splitting the problem into subproblems, combining the results, which is multiplication, etc. Okay, so if n greater than 1, then you subtract, right? So that is the subprobleming overheads. And what is the aggregation overhead? The multiplication. So all those things say I'm assuming 3 as the units required. So now the time complexity of problem of size 4 is the time complexity of problem of size 3 and you add 3 to it. Okay, and it keeps going further down. T of n minus 1 plus 3 is T of n minus 2 plus 3 plus 3. Okay, as you keep going, you will reach T of n minus k plus 3k. Now you have to come to T of 0, right? T of 0 is the base case. When you reach T of 0, how many times you added 3 is the question. Okay, so in case of n minus 1, you added only 1 3. In case of n minus 2, you added 3 twice. So in case of T of 0, how many times you added 3 is the question, and that is the time complexity, correct? So for T of 0, I must assume n minus k is equal to 0, right? So if it is T of 0, then how many times I added 3 is the question. So let's assume n minus k is 0, which is the base case, the exit condition. So when n minus k is 0, what will happen to T of n? T of n will be T of 0 plus 3n, because n is equal to k. N minus k is 0, so n is equal to k. So this statement becomes T of 0 plus 3n. As we know, T of 0 is 1, because I'm just returning 1. So it is basically 3n plus 1, and it is upper bounded by n. So you're running this algorithm for an order of n times, not more than that, or not lesser than that. It's order of n. So you are easily able to arrive at time complexity of a factorial, which is order of n. It is 3n plus 1. You ignore the constants 3 and 1. So it is order of n. Okay. So now let's try to map this to master theorem. So what is A here? So T of, say, let's say T of 4. T of 4 is split into one subproblem, T of 3, which is again split into one subproblem. So at each instant or each instance, you're subprobleming only once. So A is 1. And what is the size of the new problem? It is n minus 1. You start from T of 4, f of 4, you go to f of 3. So the size is reduced by 1. So it is n minus 1. And f of n at each point is 3. Okay, so this corresponds to master theorem very well. In case of Fibonacci number, same way. In the interest of time, I don't want to rush into these things. So if you apply the same methodology here, you will be able to get the order of order as 2 power n. And if you look at master theorem, so each time you are subprobleming the problem into 2. So A is 2, and you're reducing the size by either n minus 1 or n minus 2. One subproblem is having size n minus 1, the other subproblem is having size n minus 2. So there are two subproblems in it. Okay, and f of n is 4 because it's like one lesser than operation is there, two subtractions, and one addition aggregation is there. So I'm just giving 4 as a random number. Anyway, it's a constant which will be ignored. Okay, so let's look at Fibonacci, a different style. I'll skip this for now. The last thing, okay, by last before. So binary search. So ignore that. So in the case of binary search, each time you're again subprobleming to only one subproblem. Okay, because you go to either left or you go to the right. You don't go to both the trees. You go to either the left subtree or the right subtree. So A is 1, and every time you reduce the tree size by half. So B is 2. So if n is 8 initially of the original tree, the number of nodes. Now when you go to the left tree, the number of nodes of the tree becomes almost half, which is 4 or 3. So B is 2. For the second subproblem, the size is half of the size of the original problem. Okay. So this is the last one that we're going to see today, merge sort. The merge sort, the complexity is n log n. Let's see how it is arrived at. So this is merge sort algorithm. So during each merge, say when the list is split into smaller lists of each containing size 1, after that you merge all these sorted lists. For example, when you have to merge 38 and 27, you have to make one comparison. If you have to merge 2738 with 3 and 43, you will have to make 3 comparisons at the maximum. So during each merge, n minus 1 comparisons are required, where n is the size of the combined list. So if you have to combine 2 lists of total size 4, then you have to make at least 3 comparisons or maximum 3 comparisons. Okay. So let's look at how the complexity is arrived at for this. So T of 1 is 0 because when the list is only one element, then it's 0. We have to do nothing because no comparisons are required when the list has only one item. So now let's apply the same master theorem. So T of n is basically T of n by 2 plus T of n by 2 plus n minus 1. How is this arrived at? Time complexity of a list of size n is the time complexity of list of size n by 2, which is the left list, the time complexity of list of size n by 2, which is the right list, and n minus 1 is the number of comparisons you need to merge these two lists. Okay. So when you keep going, it's like 2 times T of n by 2 plus n minus 1. And again, you apply the same T of n by 2, which becomes 2 times T of n by 4 plus n by 2 minus 1, and so on. So when you generalize this, you get something like this: 2 power k times T of n by 2 power k plus k times n minus c2, some constant. Okay. Now, what is the exit condition? When there is list with only one element, which means n by 2 power k is 1. The last t of n by 2 power k. So I want t of 1. So n divided by 2 power k should be 1, which is k is equal to log n. So when you substitute k with log n, the last statement, you get t of n, which is equal to 2 power log n times t of 1 plus log n star n. T of 1 is 0, so it is n log n. So in case of merge sort, A is 2, because every time you split the problem into 2 subproblems, and whenever you split the subproblem, the size of the subproblem becomes half of the original problem. So B is 2. F of n in this case is n minus 1 because you have to make 3 comparisons during merge or aggregation. Okay. So with this, I end this session. Thank you so much for attending. Before I conclude, I just want to reiterate on the fact that unless you practice solving problems using recursion, you cannot master recursion. And unless you master recursion, you will not be able to decide on which is the best approach, either iterative or recursive, for a given subproblem, for a given problem. Okay, so please try to solve more problems using recursion, even if you're comfortable with iteration. So try as many problems as possible, solve them using recursion, and do it all by yourself. Do not look at internet or consult with your friends. So that will help you master recursion. Okay. Thank you so much. In case you are interested in this topic and the overall problem solving course, which is a 2-day course, you can reach out to GUVI. They can help you on the next steps. And sorry for rushing through. I thought I should give awareness of many things to you, especially the time complexity. So I'm sure not everything would have been very clear and understandable, but as long as those are like kind of awareness to you, I'm very glad for doing that today. So please explore all these topics further, or reach out to GUVI for further information. Thank you so much. Thanks for attending.
Hi all, this is Harun representing GUVI. Thank you, Mr. Ramkumar, for this wonderful presentation. I hope it was very helpful to everyone, and everyone actually seems to be very interested. Thank you, Mr. Ramkumar, for this session doing with GUVI.
Thank you so much, Aaron. My pleasure. Thank you.